So, hi everyone. Today we're solving a pretty interesting problem. This is actually one of my favorite problems with the handout. It's problem number 4 of Kevin Zhou E1. And it's about a system of point charges, a system of particles, which is in equilibrium, meaning each and every charge in the system has zero force on it. And we want to prove that the total potential energy of the system is zero. So, very interesting problem. There's a very specific type of trick to it, which is pretty hard to see. Now, how we're going to be solving it is thinking about the definition of potential energy. So, if you have a particle here, and we want to bring another particle to this particle exerts a electric field in every direction. Let's say it's a positive point charge, and the potential energy of this particle in the system will be sort of the energy needed to bring it in from a point infinitely far away to here. And the actual expression for this potential energy will be the integral of the force on the particle dot producted with the infinitesimal distance along the path. So let's say this is our point charge that's exerting electric field. This is the particle out at infinity. Whatever path we take to get over here, whatever weird chaotic path we take, we can find that this is the dr vector along this point, and the force vector will be sort of the okay. I drew this a bit. I chose a very bad point for this, so let's choose this point. The dr vector will just point tangentially to the curve, while the force vector points towards the point charge, and the dot product between these two vectors gives the potential energy, or the like increment to potential energy from that point, and all those integrated together gives us the potential energy. Now, the reason this formula is here, we're not going to be doing any computations. That would be ridiculous for this question. There is a very, so we want our potential energy to be zero, right? There's a very particular case where the potential energy from this can be zero. Okay, one way is if we want this dot product to be zero at every point for this potential energy to come out to zero. That's the simplest way to get a zero potential energy. One way is if force and the displacement dr are perpendicular to each other at every point, a 90-degree angle, because the dot product of two vectors are orthogonal 90 degrees to each other are zero. This isn't really going to lead us anywhere, because then you'd have to make a sort of weird path where the force is 90 degrees at every point, and it's just a dead end. Another way is if one of these things being uh, multiplied using a dot product is zero. Making dr zero is nonsensical. So what if the force in this product, the force of this potential energy, was zero at every point? If the force along every point on this path is zero, then our potential energy comes out to zero. Now, obviously, for this path with one point particle, another particle coming from here to there, there's no way force is going to be zero, because this positive charge exerts a positive force at every point along the path. But if we happen to have a system where each like small particle experiences zero force, which is the setup here, where the setup we have is a bunch of particles in equilibrium with each other, where each and every particle experiences zero force in this setup. So that means that with this setup in mind, what we want is for the force to be zero along the path for these particles to get here. Like if we're pulling this particle from infinity to here, we want the force at every point on the path it takes to get here to be zero, so that the potential energy can end up being zero. And there's a very interestingly, okay, so I'll erase everything so I can show you this. There's a very interesting way to ensure that we have a path where the force along it is zero at every single point. That way is if I just use this good notes trick to uh I deleted my whole thing. Oh no. Okay. Technical difficulties here. Um, if we resize this, right? At this for this setup, the force is completely zero on each and every particle. So we want a situation where coming into this configuration, each particle is experiencing zero force at every point. If we make these particles way larger, if we can sort of compress this system so that the ratio of the distances between the particles remains the exact same and the particles are just being compressed into like a smaller area. What this means is since the ratios between the forces are still the same, the forces of these particles on each other still cancel out, and these all these particles are going to have zero force on them. And the way we're getting them in from infinity is we have this setup with the particles at the same distance away at infinity, and we sort of compress them together in this sort of way where the ratios of the distances and the sort of setup of the system is the same. It's just that the distance between them is decreasing. Sort of you're basically applying a smaller and smaller scale factor to your system. That way, the forces on each and every particle at any point in this journey from infinity is still going to be zero. And that means that the potential energy is going to be zero, which proves that if you have a system in equilibrium, its potential energy is zero, because you can always do this trick where you bring them in from infinity while keeping the ratios of the distances between them in such a way that they're in equilibrium, so that the forces on each particle is zero and we get zero potential energy. And that's the solution to this question. And yeah, that was this question. So thank you so much for watching. I'll be doing more questions on E1. Hopefully we'll wrap up E1 in the coming week. And yeah, thank you. Bye.